So we have a lot of different things going on in an inclined plane problem. And as always with multiple forces, you really need to start with the free body diagram. So we have a trunk weighing 652 newtons resting on a plane inclined at 35 degrees above the horizontal. And it's asking what's the coefficient of static friction between the trunk and the surface of the plane. The plane is just any straight surface. So it's a very generic term. I'm going to draw my plane, my straight surface. And I always draw my planes, my inclined planes, slanting that direction. You can draw them the other direction. It really doesn't matter. I just draw it that way out of habit. So here's our trunk. And we know that this force is due to gravity and is 652 newtons. And we know that this angle is 35 degrees. That's all the information we're given in the problem. But the rest of it you should be able to know. When there's an object resting on a surface of anything, there is normal force. And while gravity is always straight down to the center of the earth, normal force is always perpendicular to the surface. So here's the surface, and it's perpendicular. So that's as close to a right angle as I can successfully draw. And there's the normal force. We also know that it is static friction keeping this trunk from sliding down the hill. Friction is always in a direction to oppose motion. So we have friction. So now we have all three forces that are involved in this situation. But we can see that they're not all in the same dimensions. F of G is in the y dimension, and N and F are in between. So we have two options here. We could break N and F and the motion of the object all into x and y dimensions. Or the much easier option is tilt your head until it looks like this. And then, all of a sudden, all you have to do is break f of g into x and y dimensions. And then the motion is all happening on the x dimension along this plane. All the motion's happening in the x along this plane. And the normal force is in the y. And the force due to gravity has a component that is in x and y. So, tilt your head. When I tell you to tilt your head to look at the problem, this is what I mean. Let me put this back to normal first. So we can draw our gravity force broken out into x and y components. We have FGX. Tilt your head. FGY. I always label my right angle because these sometimes get a little wonky and not really straight lines. So label your right angle so that you know which is which. Now this 35 degrees tells us something in our triangle. And some of you can just look at it and see it, but I'm going to go through the explanation this once to explain how we find this connection. We can see that this is a right angle. So if this is 35, then this has to be 90 minus 35. So it has to be 55. And if this is 55 in this blue triangle, then this down here has to be 35. So you can always just remember that this angle goes here as well. And this is why. I want you to understand why, but you don't have to go through that process every time. You can just know that you understand why, and it goes here. So we can talk about the X and Y directions now. So the sum of the forces in the X direction is equal to 0 because it's resting. That means it's not moving. So this means, and you can see it if you tilt your head fairly clearly, that these two are going to cancel each other out. So Fgx is equal to the friction force. And we can see that the sum of the forces in the y direction is also equal to 0, which means that the normal force is equal to Fgy. Now we are asked to find the coefficient of static friction, which isn't a force at all. It's μs. There's only one equation with that in it, and it is F of friction, static friction, equals the coefficient times normal force. So in order to solve for this, we need this value and we need this value. So our first step is almost always going to be, after we do all this, to break this into its X and Y components. So we can see in our triangle here, if this is 35, then the Y is adjacent. So, TOA. And our X is opposite, so we will use sine. The sine of theta equals opposite over hypotenuse. So we get that opposite is equal to 374 newtons. And that this is also equal to the frictional force based off of this, our logic from looking at our free body diagram. To get our y, we see that it is adjacent, so we will do cosine of theta equals adjacent over hypotenuse. So we get that the y component of our weight is equal to 534 newtons, which is also equal to our normal force. And now we have the information we need to plug into this equation. So friction is equal to our coefficient of friction times our normal force. So our frictional force is equal to our coefficient times our normal force. And when we divide, and we round to the appropriate three significant figures, we get that the coefficient of static friction is 0.700, and it's unitless because our newtons cancel each other out. So none of this math is new. All of this math is a review from previous chapters. And none of it is very hard math. The hard part is this free body diagram and then understanding right here what this free body diagram tells us. The logic is the hard part in these problems. You need to be able to do this step. That's why I made you guys practice free body diagrams earlier, and why you need to draw one for every single one. With your work, I want to see your free body diagram. That way I can help figure out what's going wrong. So please do your free body diagram. I want to see that as part of your work.